Hey, so I wanted to check in and look at one of these homework problems in 1.7 inverse functions. It talks about these three problems here, 13 through 15. It says, for the following exercises, find a domain on which each function f is one-to-one and non-decreasing. Then it says, write the domain in interval notation and find the inverse of f restricted to that domain. So, what are they talking about here? Well, if you remember, in order for f to have an inverse, it has to be one-to-one. So f has an inverse if and only if f is one-to-one. So to have an inverse, you have to be one-to-one. If you're one-to-one, you have an inverse. So if we look at any of these three functions, so let's look at the second one, f of x equal x minus 6 squared. If we look at that function, that is a quadratic, and those quadratics are not one-to-one. So it would not have an inverse. And if we thought about what the graph of this looks like, this would be y equals x squared moved to the right 6. So I could graph that. I hit a button with my pen, excuse me. Fix that. Okay, so we could graph this, set up a grid, moves x squared, moves to the right 6. So I'm just going to put 6 over here somewhere. This is a opening upward parabola with the vertex over here at 6, 0. So there it is. And this is not one-to-one. It fails the horizontal line test. Just draw right across there, because that horizontal line crosses the graph more than once. So in the homework, what it's saying is, so this function would not have an inverse. So if we go back to this homework, what are they talking about here? They want to find a domain on which the function is one-to-one and non-decreasing, or sort of think of non-decreasing as increasing. So on which domain is f increasing? Well, f is increasing from 6 to infinity, an open interval from 6 to infinity. But it's non-decreasing on just that closed interval from 6 to infinity. So if we take f of x and we instead say, okay, it's the same function, but I want to restrict the domain to be x greater than or equal to 6, then this graph starts over here at 6, and then it's just this half of the parabola. And on that half of the parabola, this new function is one-to-one and hence has an inverse. So how do we find that inverse? Well, finding that inverse is the same steps as before. Let's see if I can put this more central here. And I'll go back to black, and we'll find this inverse. So for this function that is now one-to-one, set y equal to the function, swap x and y. So we get x equals y minus 6 squared. We're solving this for y. So to solve that for y, I'm going to rewrite it here. We need to square root both sides. And when I do this, normally on the right side of this equation, I would get an absolute value equation. But we have this restriction up here that x is greater than or equal to 6. When we swap x and y, we get this restriction that y is greater than or equal to 6. And here, if y is greater than or equal to 6, then this y minus 6, the reason we need absolute values is to make sure this is positive. But if y is bigger than 6, then y minus 6 is already greater than or equal to 0. So this will have to equal the square root of x. In other words, this allows me to not have absolute values because we just want the one solution, the positive solution, which this will be a positive solution. And then we add 6 to both sides. And we get the inverse function because we've isolated y here. Square root of x, I need to be careful. You know, the square root ends, and then we're adding 6. Square root of x plus 6, and that's the answer to this problem. F inverse of x equals the square root of x plus 6. Okay, so I want to look at, even though this problem doesn't ask me to graph these two functions, I want to look at the graphs of these two functions, or really the graphs of any two inverse functions. And just recapping here, the way they worded this is a little bit strange. Back on the homework, it said, find the domain on which f is 1-to-1 and non-decreasing. They just want the half of this parabola, the half that's increasing, which is from 6 to infinity, or x greater than or equal to 6. Okay, let's look at these two graphs, the graphs of these two functions. So the original function, f of x, was x minus 6 squared on the domain x greater than or equal to 6. I'm going to be a little more precise if I can by drawing a grid here. 4, 5, 6. And then x greater than or equal to 6. I'm going to draw it in red here. Can I go through 6, 0, and then 7, 1, and 8, 4. It's going to go up like that. There's my parabola going up. So the actual points there, not the shifted points, but the actual points are 6, 0, 7, 1, and 8, 4. You could plug these in here. 6 minus 6 is 0, squared is 0. 7 minus 6 is 1, squared is 1. 8 minus 6 is 2, squared is 4. I just want the actual points on F. Then I want to draw the line y equals x, which is the line that goes right up the diagonal here. The slope 1, y equals x. Because it turns out the graph of the function and its inverse are symmetrical about this green line y equals x. And why is that true? Well, when we want to graph the inverse, I don't even need the formula for it. What I can do is just take the value of the function point there. Let's use a different color. I find something that's clearly not red. Let's go purple. We take the points from F. To get the points for F inverse, we just take those points and we swap the values. So instead of 6, 0, we get 0, 6. Instead of 7, 1, we get 1, 7. Instead of 8, 4, we get 4, 8. 0, 6, 1, 2, 3, 4, 5, 6 is here. 1, 7 is there. And 4, 1, 2, 3, 4, 8. Be here, and this guy comes out like that. So the purple graph is F inverse, the red graph is F, and if we think about what we just found with F inverse of x from the previous page, this was equal to, we had the formula for it, the square root of x plus 6. And we think about what that graph looks like. It's the graph of the square root of x moved. What does that do? Moves it up 6. And then we can sort of see, if I extended both these graphs, they would cross on this purple line over here somewhere. Well, let's not do that because my graph's a little up. They're going to cross here. You can't see me pointing at it. They're going to cross on that green line in the middle. And if you folded that green line, these graphs should look the same. Exactly. It's a little hard to see on this just because my scale, I lost a bit of my scale here in the y direction going up there. I need to go a little higher. There we go. And that makes it look a little easier. Okay, let's do one more. So I'm just gonna copy this page and we'll do another example. Let's start off with a function f of x. Let's do another square root. Square root of x minus 2. I'll just do that one. So this is the graph of the square root of x moved to the right 2. And again, I want to graph my basic points, but I know what they are, so I don't have to list the basic points. What I can do is graph them. So what would those basic points be? 0, 0. And then 1, 1. And then 1, 2, 3, it'd be 4, 2. So it'd be one more tick mark, 4, 2. And that is the square root of x. Move to the right 2. And what I want to do is actually list the actual points there. So not the shifted values, but the actual points from f. Here, and I'll just do it right beneath this. For f, what 3 points did I just plot? When x is 2, y is 0. When x is 3, y is 1. And when x is 4, y is 2. Then I want to do the same thing over here for f inverse. Take those x and y values and swap them. So you're going to get 0, 2, 1, 3, and 2, 4. And then really before I plot these numbers, I'm going to first plot the line y equals x right up the diagonal. So again, this is just a line of slope 1. It should go through all the corners of your graph paper right up the middle, where x and y are equal. So 0, 0, 1, 1, 2, 2, etc. And then 0, 2 is here on the y-axis. 1, 3 is there. And 2, 4, 2, I think I got this one wrong. 1, 2, 3, 4, 5. This should be 6. Sorry. That should be a 6, 2, which makes this other one also a 6, 2, 6. Sorry, that point is 2, 6. So, or 6, 2. And so on here, 2, 1, 2, 3, 4, 5, 6. I need to go a little higher. A little higher on my grid. 5, 6. And go back to purple. So 0, 2, 1, 3, 2, 6. Gonna be a little higher. And there's that guy. Now this is a little easier to see. If we were to fold this along the line y equals x, along the green line, the red and the purple graphs would coincide. Here they don't exactly because my scale, you can see my scale up here got a little bit off. it's hard to do without graph paper. So it's easier on graph paper. And there's my two graphs. And then notice this is half of the parabola, what we just drew. If you go back to the last function, we started with the red one, it's half a parabola. And that was this restriction on the domain. So now I want to look at actually solving for F inverse. So I'm going to restart here in black. If my function F is equal to square root of x minus 2, how do I find F inverse? The formula for it. We've already graphed it. So step 1, set y equal to the function. Step 2, swap x and y. So this becomes an x equals the square root of y minus 2. Step 3, solve for y. So I'm going to scroll down. I'm going to rewrite this last step here so you can see it. X equals the square root of y minus 2. So I have to get rid of this square root. So I'm going to do that by squaring both sides of this equation. And here I do not introduce an absolute value. What I get on the right side here is just y minus 2. But I'm going to have to restrict my domain later because I'm losing information. When I square this square root, we're losing some information. And I'm going to show you in a second where that goes in. So then I get y is equal to x squared plus 2. And that is the graph of y equals x squared moved up 2. Clearly, that's not what we have in this picture because this is only half of the parabola. This has a restricted domain. So how could we see that without graphing it? We'll come back down here. And step 4 is to set this equal to f inverse of x. F inverse of x equals the result. And if that result is not one-to-one, we have to restrict the domain. The domain of f inverse to equal the range of f. So in this problem, what that means is my f inverse of x is this formula, x squared plus 2. But this is not one-to-one. So I'm going to put a comma, and I'm going to restrict the domain. And how do we restrict the domain? The domain here for the inverse needs to equal the range of the original function. So if we look back at our original function, switch here to red. If I scroll back up and I ask what's the range of this function, the square root of x minus 2, the range is the y values here. So the range of this, y would always be greater than or equal to 0. Or if you go back to the original picture, you can see the red. The range of the red is that y is greater than or equal to 0. When you swap x and y, you get the domain of f inverse, which is that x needs to be greater than or equal to 0. And you can see that in the picture as well. The purple graph is x squared plus 2, the whole parabola. We only want half of it, the half to the right of 0, or when x is greater than or equal to 0. So this restriction, or this range of f, becomes the domain of f inverse. I don't think there's any of these on the homework going this direction, but it is something we need to be careful of. And basically, if you think about all of our basic graphs, there's only sort of 3 that are not one-to-one. It's the absolute value of x. Okay, we're probably not going to run into that for inverse functions because it's piecewise defined. The other 2 are 1 over x squared and x squared. So really both of those you could think of as having an x squared in them. So the only problem that we're going to have is when we have quadratics, the x squareds. 1 over x squared would also be a problem, but I don't think it shows up very often in terms of needing to restrict the domain for those. Primarily, it's going to be these quadratics. And then again, we'll do it again in Math 142. We'll restrict the domains of the trigonometric functions so that we can define their inverses. Okay, that guy's done. I'm going to sign off. Just a few notes from 1.7, mainly dealing with these ideas of why this problem in the original is worded so strange, because this original function does not have an inverse because it's not one-to-one. So in order for it to have an inverse, you have to only look at half of it. Then we can, by restricting that domain, we can then find its inverse, and we found it here. Notice this bottom thing already is one-to-one, so I don't have to restrict the domain on that original problem. Then I looked at the graphs of both of those, and those graphs are symmetric about the line y equals x. And then we did one more problem where we started with a square root, which was one-to-one. That's the red graph. And then we graphed the purple, which is symmetric about the line y equals x again. And those graphs sort of show us, this is only half the parabola. So when I go to solve this guy, square both sides, that is no longer one-to-one, this x squared. And if that result is not one-to-one, you have to add in the restriction on the domain. All right, hopefully that will help, and I'll sign off.